tell us about your research in the formation of tornadoes?
Yeah, so I mean, my tornado research has gone back to the time that I was a PhD student. I went to school at the University of Oklahoma, and I started this work back in roughly like the 2011 era. And first got started using rapid scanning mobile radar observations to study the processes and the evolution of tornadoes as they form back then. And noticed with like the one case that I really focused on for my PhD, that it really didn't seem to have a traditional top-down formation when you look at the evolution of how the rotation was developing with time. And I only really used one metric for that particular study. And then a couple of years later, so I kind of did that work, and then I kind of moved on from it. And then a couple of years later, I was reading a paper written by a colleague of mine about a tornado that I had also written about in the context of radar data. And I noticed that in his paper, he listed a start time that was like 2 minutes earlier than what we thought happened with the radar data. And 2 minutes doesn't maybe seem like a lot, but in the context of a tornado that's evolving very quickly, it's pretty substantial. So I was kind of curious, like, what's going on here? What's this discrepancy? And I realized that, so his study was entirely based off of visual observations. Okay, not entirely, but they were attributing the time of tornado formation based off of what people were videoing and photographing. And there was basically, photographic evidence of what you would look at and call a tornado. And this was present like roughly 2 minutes before, so this is the time that the tornado formed. So that was a real head scratcher for me. And it was like, what's happening? And it turns out, when we did our analysis, we defined tornado formation as basically the time when strong rotation was present over a relatively deep layer of the atmosphere. So basically you could think about it maybe like from the ground to, a kilometer is on the order of, three quarters of a mile or so above the ground. And when I kind of looked at the data in a little bit greater detail, I noticed that at the very, very bottom, the data that were from the lowest elevation that we collected the data. Sorry, I'm back. Give me 1 second here. Hey, girls. I need everybody off devices. Because I need to be on this Zoom and I can't, it just cut out on me. All right, everybody turn off streaming, please. Sorry, this is what happens when you have kids at home and everybody's trying to use the internet. Oh, goodness. All right, I'm trying to strategically figure out where the best place is going to be for me in the house too. So I'm going to just give you a little bit of a tour of my house for the moment, and I think I'm going to go upstairs. I'm going to be in here, okay?
Okay, I need to grab some.
So what did you hear out of that? I don't know where it...
We heard about like the visual, the research that was like stemming off of pictures and stuff, and then kind of what you were like, what can I build off of that?
Yeah. Okay. Yeah, so basically determined that we missed data from the lowest elevation angle. And that was really what... so basically there was a tornado at very, very low heights. So we're talking like, maybe 100 feet or so off the ground. And then even a couple 100 feet above that, there really wasn't any evidence to suggest that there was a tornado at that point. So, so that was kind of like a little bit more of an eye opener, and like, oh, we've got something interesting kind of going on here. Let's give this a little bit more investigation. So after that particular case, I expanded it to 7 other tornadoes and was basically like, what can we see with these 7 other tornadoes? And they were of varying intensity. Some of them were weak, some of them were stronger, and found that essentially none of them really showed a good, strong signal for the traditional kind of top-down formation, but rather they almost all extensively or exclusively like showed either bottom-up or kind of like a scenario where everything kind of comes together all at once. And you go from basically not having a tornado to having a tornado over a vertical depth of 1 kilometer or even larger in some instances, a time frame of maybe 30 seconds. So it's happening really, really quickly. And in many cases, we actually have this really strong rotation at the ground first, or very near to the ground. And that actually kind of almost gets sucked up. Like you can almost sort of think about it like as a vacuum cleaner, like you have this really strong rotation near the ground, and then there's upward motion above that, and it kind of gets sucked up into the top part of the storm. We just kind of visually cue in on the funnel cloud because that's what our eyes see. And there's also, it's that atmosphere up there is more saturated. You're closer to reaching like 100% relative humidity higher above the ground than what you are at the ground. So you condense your rotation first high up, even though the same amount of rotation is actually present throughout the depth of the layer there.
That's one of the things you said that I thought was so interesting was that most of the data that stemmed from the original study was like from pictures. And I think just the other science that we've learned in high school, it's been like so theoretical and like looking through microscopes, but with atmospheric science that you can like actually see it with your own eyes, like that's something I just happen to love.
Yeah, absolutely. And I think it's something that makes our science very unique and very kind of tangible and applicable, because you can go out and you can visually observe a lot of these processes and a lot of the things that are going on, especially when you have something that's relatively rapidly evolving, like thunderstorms and tornadoes, things like that.
Totally. Yeah, it's really great. Our next question is, what does your research entail?
So what I have to do is basically use a radar that's mounted on a truck and take out the truck, and we go storm chasing. So basically take the truck out to the areas where we think storms might form later in the day. It kind of all depends on the day. It depends on where storms are forming with respect to where we start during the day. Sometimes it's kind of like just hang around and then decide where to go in the afternoon. And once storms start forming, then you just kind of go and pick a storm. Other times you have to sort of preemptively say like, okay, we were traveling 8 hours today. We have to leave early in the morning, and we have to anticipate that storms are going to fire in approximately this area. And you have to really be conscientiously thinking about how you're going to get to where you're going to get to, where you think the greatest likelihood of storms that may produce tornadoes ends up actually being, because, you can make a decision to go northwest versus, due west or due north, and ends up putting you 3 hours between your separate potentially, end points there. And that's going to make a big difference when you go to actually scan the storm. So we try to position ourselves in a location where storms are starting to form, where they're kind of getting to a mature point and are kind of nearing the time frame in their life. Most tornadoes don't form like right as a storm is forming. They form, an hour or so into the lifetime of the storm. So it's helpful in a sense because you can sort of see where storms are starting to fire and kind of anticipate their forward motion and get yourself set up. But it's always really hard to know which storms are going to end up producing tornadoes. So in that sense, it's a little bit of a roll of the dice. But we take this instrument, we set up the instrument, and then we basically collect data. So the radar works by sending out electromagnetic energy into the atmosphere. It hits things like raindrops and hailstones, and it scatters back to the radar, and we can determine information about the speed of our raindrops or our hailstones or whatever it is that we're sampling, as well as their intensity. And we can even detect differences between tornado debris versus rain or like meteorological targets instead. And we can detect even a little bit about like the shape. If we have something that's a circle versus something that's kind of flatter, we can actually detect some of those differences as well. So we use all of that information kind of put together to come up with a storyline essentially of how the storm is evolving and what processes might be occurring in the storm.
Really interesting.
Yeah. When you travel, like, for the storms, do you stay in like the area that's local to you, or do you ever like fly out somewhere to observe like a specific storm?
Yeah, that's a great question. So I'm physically located in Ohio, so there's not a lot of tornadoes in Ohio. So I have collaborations with the University of Oklahoma, and so my storm chasing experiences, if I'm acquiring data or using data, are going to be kind of collaborating with them. So that means that I'm either flying or I'm driving out to central Oklahoma to meet up with them, and then the sort of geographic domain that we have tends to be in the central Great Plains, sort of the traditional tornado alley states, Texas, Kansas, Oklahoma, Nebraska areas. And that's really because with a mobile radar, you have all kinds of challenges if you have things like hills or trees or buildings that are impeding your line of sight between where you are and where the tornado actually is. So a radar can't scan through a tree, for example. So if you have a big tree or a phone pole or something like that in your way, it's going to totally block your data. So you want to keep data collection occurring in an area where it's relatively flat and open, and the Central Plains are, obviously a good choice for that.
Right. We saw that you teach as well. So do you like enjoy the balance between teaching and doing research?
Yeah, absolutely. And that's why I am at a university, because I do really enjoy teaching a lot. And I started my career at another Ohio institution, which is Ohio University. And now I'm at Ohio State. So they're actually two different institutions with very similar names. But Ohio University had a even kind of stronger commitment to teaching. And I started my career out teaching 4 courses a year, which is, from a college perspective, is a pretty decent number of classes to be teaching, because they're all different classes. And I absolutely love teaching. I like to mentor students. I like to explain material to students and get them excited about what they're learning. I incorporate a teaching style that's very much of like an active learning kind of a strategy, where students are answering questions, where they're discussing with each other, and kind of really engaging with the course material that way. And I actually have, in the past, led students in an instructional experience in the field where I take them out storm chasing. So we actually do have like students go out storm chasing with me, and we kind of walk through the whole process of how it works, and they get to help out with the forecasting, and they're viewing how things are changing throughout the course of the day. And ultimately, hopefully seeing something cool in the weather too. But I also really enjoy the research side of things too. And as I've kind of gotten further in my career, I've decided that I want to be able to have a little bit more flexibility with my research time, and have a little bit more time to do research, which was what kind of inspired me to change to Ohio State, which is a little bit more research focused, a little bit less heavy on the teaching. So I still do both, and I still really enjoy doing both. But this gives me a little bit more of an opportunity to explore additional research opportunities.
That's awesome. Do you find that most of your teaching is with undergraduate students?
So thus far into my career, yes. And the classes that I'm teaching are predominantly undergraduate courses. Most of my classes have on the order of about 20 people or so, 20 students or so, and they're upper level courses. So we're talking, junior and seniors in college are taking these courses. So yes, the majority of my students are undergraduates, but I do mentor graduate students. Ohio State has a master's degree and a PhD program, whereas Ohio University just had a master's degree. So I've had like, I don't even actually remember what my count is, something along the lines of like 10 to 12 master's degree students. And I'm now kind of positioned to take on PhD students. And then I also have undergraduates who have done formalized research for me as well, like outside of the classroom. So they have specific like honors theses or department projects or something along those lines, or even just independent study to do work with me.
That's awesome. And then our final question is, why did you choose a career in atmospheric science?
It's really funny because I don't know. I mean, I don't know what your history is for either of the two of you, but in meteorology, we kind of joke that we're like genetically bred to study meteorology because like almost like, probably 90% of the people who I meet in the field all have a similar story in the sense that like it's all something we've all been totally interested in since we were young kids. So for me, I just had this interest in the weather from a very early age. And, I can remember probably being like 6 years old or something like that. And my cousin and I used to stand on the back deck of my parents' house, and we had a little thermometer and a rain gauge out there, and she would pretend to be the camera person and I was the meteorologist, and I would like look up at the sky and identify clouds and then like look at the thermometer and say, oh, and it's 72 degrees out, and we had an inch of rain overnight or whatever the Okay, I'm back.
Yeah.
So it's just been something that I've been really passionate about since I was a child.
That's awesome. I think that like overall atmospheric science is one of the most interesting courses I've ever taken at our school. And I think that especially just the way that there's so many different topics to cover. Like earlier in the year, we were talking about climate change, and now we're talking about reinformation. Like, I just love how there are so many different possibilities of things that you can study. So yeah, I'm so thankful for all of the information that you told us today. It was truly
absolutely
awesome.
Yeah, and feel free to reach
much.
out if you ever have any additional questions in the future. I'm happy to, and I'm happy to hear that you guys are getting atmospheric science in high school. That's awesome.
Yeah, it's definitely a privilege. So we really appreciate all you had to say today, and I'll reach out soon.
All right, sounds good. And I will send you the link of our recording as well.
That's perfect. Thank you so much.
Okay, take care.
Bye.